Hello, this is David Zoltowski, and I'm presenting the video summary of slice sampling reparameterization gradients for AABI 2020. This is joint work with Diana Kai and Ryan Adams at Princeton University. Probabilistic objectives that take the form of an expectation with respect to a parameterized distribution p theta of x are common in machine learning, arising, for example, in variational inference and reinforcement learning. Unfortunately, the gradient of this objective with respect to theta is often not available in closed form. Instead, Monte Carlo methods are often used to estimate this gradient, and one popular class of such methods are reparameterization gradients. These apply when samples from the distribution p theta of x can be simulated by first generating samples from a distribution p of epsilon that doesn't depend on theta, and then transforming those samples through a deterministic function f that will depend on theta. With this, we can rewrite the expectation now as an expectation with respect to p of epsilon and push the gradient with respect to theta inside the expectation. However, typically, reparameterization gradients apply to distributions with a tractal normalization constant. Here we present slice sampling reparameterization gradients. Slice sampling is a Markov chain Monte Carlo algorithm for generating samples from a probability distribution, and importantly, the density of the distribution may be known only up to a normalizing constant. And therefore slice sampling and reparameterization gradients apply to both normalized and unnormalized distributions. However, since we're simulating a finite Markov chain, the gradient estimates will be biased, and the samples that are generated from the algorithm are going to also be correlated. Here I'll provide a brief overview of the reparameterized slice sampler. Imagine that we're trying to sample from the distribution given by this blue curve, where the density is proportional to pi theta of x. The idea of slice sampling is to sample uniformly from the area beneath this curve. And it proceeds typically in two steps. First, we start at some value xn and sample a value uniformly between xn and pi theta of xn, the height of the curve at that point. We do this by just drawing a uniform random variable, and that gives us a height y, which is equal to pi theta of xn times the uniform variable u1. This in turn defines a horizontal slice through the distribution, where the slice is given by the values x for which pi theta of x is greater than y. The second step of slice sampling is to sample uniformly from this horizontal slice. And we do this by numerically finding the endpoints of this slice, namely the points where the slice intersects with the curve pi theta of x. And we call these x minus and x plus, so the 2 points in the different directions going from xn. And once we identify these points by the root finder, it is straightforward to generate the next sample value xn plus 1 via another uniform random variable. It is clear that the first step of this sampler is reparameterizable, but it may not be clear that the second step is as well. Importantly, the slice endpoints x minus and x plus are implicit functions of the parameters theta, the initial value xn, the direction d, and the height y. And now, with this, we have a two-step deterministic process conditioned on the random variables u1, u2, and d. On the previous slide, we described the reparameterized slice sampler, and now we discuss computing the gradients. Here's the computational graph of the slice sampling process. If we start at an initial value x0 and then generate n samples x1 to n, at each step of this sampler, we take in some random variables and then have a deterministic condition on the random variables. Note that at each step of the process, we have a dependence on the parameters theta. And therefore, if we evaluate a loss at the last sample xn, and want to compute the gradient of the parameters theta, we have to backpropagate through the entire sampling process. I'll just allude to one detail that we had to do, which is that if we remember the reparameterized step 2 from the previous slide, and we had implicit functions for the slice endpoints x minus and x plus, this means that we need to use implicit differentiation to compute the necessary Jacobians that allow us to do the reverse mode autodiff. In the paper, we first start with some simulated experiments to verify that the slice sampling reparameterization gradients work. And we show that we can optimize the parameters phi of a variational distribution Q by minimizing the KL divergence between Q and some known target P, and that this works for both multivariate Gaussians with diagonal covariance and a 1D mixture of Gaussian distributions. And then next, we use the slice sampling reparameterization gradients to fit a variational autoencoder where the approximate posterior is a conditional energy-based model where the normalizing constant is unknown. For more details, please refer to the paper. With that, I'd like to acknowledge my co-authors Diana Kai and Ryan Adams for their significant contributions to this work. And thank you for your attention.